It's called DPC. It was invented in the early 90s, 92, 93-ish, by several groups, including one in Bell Labs. This is an algorithm. It is a distributed algorithm. It is an iterative algorithm. Now, what is an algorithm? Roughly speaking, it is a sequence of computational steps that is finite, and when it stops, it accomplishes certain tasks. In this case, solving this power control problem. It is distributed. This actually is a very fuzzy word. It's hard to exactly pin down its definition. We're going to see a very distributed solution today, and later in the course we'll see many other variants of sort of distributed solutions. But roughly speaking, distributed means that the network elements, in this case the transmitter and receivers, do not need to talk to each other too much with explicit message passing. This is also an iterative algorithm. So the near-far solution, for example, is not iterative. You just estimate the channel and then you tell the receiver what to do. It's a one-shot. But most of the algorithm we'll be looking at will be iterative algorithm. That means there's a certain time index. We usually use K or T to index the time. Sometimes it's discrete, sometimes it's continuous. Most likely will be discrete for what we'll be looking at. Okay, so I have to index this, and we hope that as time goes on, as this index K or T becomes very large, something good will happen. For example, the algorithm actually stops, it converges at a pretty good point, solving some optimization or gain problem. Alright, so that's enough background of just this one line here, an iterative distributed algorithm. So what is the algorithm? Let me write down the algorithm first. It's so simple to write down. It's just one single line, and then let's intuitively look at it before moving on to mathematical analysis of it. So what's the algorithm? Pretend that you are the transmitter of pair I. Okay, there are many logical pairs. This is you, your intended recipient. And the intended recipient will measure the SIR all the time. Let's say discrete time, time t. And then it will feed this back to you. Okay? And then this feedback received at the transmitter will provide all the hint that you need to know. You do not need to know anything else about this whole network. Because what you'd be doing is to say, all right, I got a target SIR, gamma I. That's fixed. It doesn't vary over time. And then I got my current received SIR, which varies over time because I change my power and others change their powers. I look at their ratio. Okay, gamma I divided by SIR at time t. And I say, this is my gain parameter. I'm going to multiply my current transmit power at time t by this ratio, and that will be my transmit power at the next discrete time t plus 1. And this is true for all the pairs I. So we use this notation, all I. And that's it. This is DPC. Say, wow, that's pretty simple. Well, it's actually very simple. Okay, how simple is it? Well, let's take a look. It's simple first in communication. Right? You don't need to know anything about the network except your own target SIR, which presumably you know, and it doesn't even vary over time, and the current SIR that your intended receiver is getting. That's all you need to know. Second, this is very simple in computation, where there's only one multiplication or division, right? And then there's very simple in configuration. What do I mean by configuration? A lot of times in an algorithm, I have a lot of parameters. Gain parameters is a typical example. Step size is a special case of that. We'll see many parameterized algorithms throughout the course. But this one actually has no parameters, right? The ratio between gamma and SIR itself is the gain. You don't have to tune any algorithmic parameters. And we see that simplicity in configuration is often the hallmark of a successful technology transfer from research to adoption. Many wonderful algorithms are not used because there are too many parameters to tune, and people don't know what to do with those parameters, and they're unsure if the parameters tuned today will still be robust and good tomorrow. But this DPC is very simple in communication, in computation, in configuration. But is it trying to do the right thing? Well, intuitively it is. We're going to look at both the equilibrium behavior and the convergence behavior intuitively. Equilibrium looks actually very good, right? What is equilibrium here? Equilibrium means, in this case, we're going to look at least two more definitions of equilibrium. But in this case, just means that nobody changes from one time to another anymore. In other words, there's certain time t beyond which no one's transmit power is moving anymore. Well, whenever that is the case, clearly that means that this ratio is 1. That means everybody's SIR is exactly the target SIR. All right. So the question is, will you ever get to equilibrium? Will you ever stop? Let's think about that. That's actually not trivial, right? You think, oh well, if my current SIR is lower than my target, this gain parameter is bigger than 1. That means my next transmit power will be bigger. Well, that will help me presumably lift my SIR next time closer to gamma. On the other hand, if my current SIR is already bigger than the target gamma, then I'll rather make my transmit power smaller. Because remember, we're talking about a 2G voice call, so if I get my target gamma, I don't care if it's bigger than that or not. So I'll rather conserve power. I want a transmit power minimal way to achieve the target gammas. And this is doing the right thing. So intuitively, the direction is correct. It is sending basically a negative feedback that says, too much SIR, lower your power. Too little SIR, well, increase your power. Too little, too small, relative to your target. This is all well and good, except you're not the only one in the room, or in this case, you're not the only one in the network. There are many other transmit-receiver pairs going around here, okay, and they all think the same way. So while you are moving, they are moving too, their transmit powers, that is. So it's not at all clear that this ensemble, this network, this crowd of transmit-receiver pairs will collectively converge and start moving together. But at least it sounds plausible because the direction is somewhat correct. Now, proving that convergence will happen is not easy. In fact, convergence may not happen. You can run this algorithm and it doesn't stop at all. And that's because if everybody requires a very big gamma, gamma 1 is big, gamma 2 is big, then maybe there's no way to achieve these gammas. You can run the simple example, right? I want P1G11 over P2G12 plus N1 to be really big. I also want P2G22 divided by P1G21 plus N2. This is received SR for user 2 to be really big. And for certain G's and N's, you see that I cannot find any P1 and P22 numbers that can make both ratios very, very big. There is an intrinsic competition or trade-off among these users. So, for sufficiently large gammas, all of them being big, you can't even get convergence anyway. So you can prove because that's not true. But it turns out that we can show whenever the gammas are reasonable, that is, they are actually achievable, there is a vector of p's to achieve them for the given g's and n's, then we can prove that this DPC algorithm will converge to this desirable equilibrium. That's provably true. But to show that would take us to advanced material, and we'll come back to that after the normal period of this lecture. So intuitively, you can see why this algorithm could work, and this is such a beautiful equation here. Okay, we're going to see many distributed algorithms later on, but this is going to be one of the simplest and the most often used.